medical QA system. This presentation is going to be delivered by Ahmed Abouzaid, Ahmed Fayed, Dina, Usama, Iman Yehia, Youssef, Amir, and myself, Ahmed Aboutaleb. This project is done under the supervision of Dr. Ahmed Rafea, Dr. Nouri Sakr, and engineer Ayman. This is the agenda for today's presentation, so please give yourself a second to take a look at it. Okay, so let us start by giving you a quick recap on what are Q&A systems. Question answering systems is an approach to retrieve correct responses to the questions asked by humans in natural language. The fundamental thought behind question answering systems is to assist man-machine interaction. Such systems generate answers through incorporating both natural language processing and artificial intelligence. Again, as a quick reminder, the motivation for our project is that existing solutions have many deficiencies such as outdated, inaccurate, and/or unrelated answers. The emerging state-of-the-art technologies provide the opportunity for development of better and more accurate applications. Our mission as a team is that we aim to create a question answering system that answers questions that are provided in common speech in the medical domain, and create a new architecture that achieves state-of-the-art accuracy and precision. So, in the next slide, I'm going to be walking you through the Q&A architecture as a whole. This diagram represents the architecture of the system as a whole. The general notion here is that we move from the left side of the diagram to the right side of the diagram. So, first of all, the user provides a question, and the first step is to try and retrieve the answer from the knowledge base. So, the module named here as knowledge base retrieval is the one responsible to do so, and it does it through looking up the answer within the knowledge base. If the answer is found, then we're good to go, and the answer is provided back to the user. Otherwise, we move to the second best option, and that is looking up the answer using the BERT-BILSTM-BIGRU similarity model. So, how does that work? We have a database containing a huge amount of question-answer pairs in the medical domain. The BERT-BILSTM-BIGRU similarity model compares the user question to a set of questions from the question-answer pairs database and provides the answer of the most similar question in the database as an answer to the question that was provided by the user earlier. However, in order to avoid the overhead of comparing the user question to all the questions in the database, the question-answer retrieval module is used to narrow down the set of question-answer pairs that we are going to be comparing with. Narrowing down the options is done using keyword filtration. Based on the architecture presented in the previous slide, this raises a few research objectives and questions. The research objectives are to receive and understand the medical question in natural language, and extract important features from the questions provided by the user and the question-answer databases. Analyze these features and respond to the user questions with the most appropriate answers. So, the questions are, what are the best word embedding layers to represent the questions, particularly in the similarity model? Also, in the similarity model, what is the best feature extraction neural network that can be used? Finally, what are the best similarity matrix to calculate the similarity between the questions? And now, Youssef is going to tell you more about the knowledge graph module in particular.
Firstly, a knowledge-based system holds some clear advantage in providing targeted responses to well-defined questions, and thus is a convenient and reliable approach in implementing a question-answering system in knowledge-centric domains such as medical fields. A predominant type of medical question seeks examination, symptoms, causes, and prevention of specific diseases. Such questions can be solved using a knowledge representation approach such as RDF queries, as RDF triplets in knowledge graph can well represent the complex connections between entities. Therefore, it's natural to adopt a knowledge graph as an integral part of a question answering system. The knowledge graph is implemented through the Neo4j graph database. It scales to 6 properties: name, description, cause, prevent, accompany, and cure way; 3 entities: department, disease, and symptom; 5 relationships: have symptom, accompany with disease prevent, disease cause, and disease cure way. The implementation of the database into the graph enables the system to create nodes and relationships between them. These 5 relationships between the entities and other properties can overall answer 6 kinds of typical questions. As just mentioned, the knowledge graph is the first layer of our proposed architecture. The whole process of the knowledge graph system goes as follows. The user inputs the question. Then the system will extract the entities with the disease symptom extractor and get the user intention by the intention recognizer. If the knowledge graph algorithm couldn't detect the disease or symptom entities, or failed to capture the user intention, in other words the purpose of the question, it would forward the question to the semantic calculation module. It will be discussed later. Then, on the other hand, if the knowledge graph succeeded in extracting the entities and the intention data from the user question, queries will be formulated to select the answer from the knowledge graph. And finally, the raw data fetched from the query will be purified and returned to the user in natural language form. Here's an example of how a question will be parsed and answered through the knowledge graph. After the user enters the question, what are the symptoms of a cold? The question goes into two different modules. First, the entity extractor will extract the entity cold. Second, the intention recognizer will detect the relationship has symptoms. Then these two results gets combined to obtain the answer for the question, which is fever. And finally, that answer will be returned back to the user. Now my colleague Ahmed Abouzaid will talk to you more about the tag filtration.
So in order to optimize the similarity calculation of each question in the dataset with the user entered question, we've designed the keyword filtration algorithm to extract the keyword using NL toolkit and select all matching keywords from our database that include the keyword and the synonyms of each and every question in our dataset. Then, the SQL query selects the most 5 relevant questions based on the number of keywords included in the matching questions. Accordingly, the most 5 relevant questions are passed to the similarity model to calculate the similarity score with the user question to select the most relevant question and its corresponding answer. So, the semantic similarity model is an improvement over the already existing model that we discussed in the previous presentation, which is called HPAM. The architecture is a layered approach in which the questions are converted into the respective embeddings using BERT as the first layer. These embeddings are passed to the BERT-BILSTM feature extraction layer to give more weights to the most important part of the questions. Finally, the semantic similarity score is calculated using the function of 1 over the exponential function of Manhattan distance. Starting from the first component, which is BERT, it is applying the bidirectional training of transformer. It also utilizes the encoder section of transformer encoder-decoder model. The encoder receives the word sequence and generates embeddings simultaneously using the 12 layer of transformer encoders to generate the embeddings. Also in our model, we used the already pre-trained state-of-the-art BERT model to generate embeddings. Therefore, the similarity model incorporates the encoder-decoder block like BERT-BILSTM to solve the problem of vanishing gradient. A self-attention layer can be then added to the top of the encoder-decoder layer as a guide to extract the sentence embeddings while introducing extra information. Then, BERT-BILSTM layer is utilized in our model to capture the semantic level connection in the sentence, and the attention layer to extract the input keywords. The structure of the layer is based on HPAM model and the Siamese LSTM framework. This is through implementing the 2 layers of BERT-BILSTM and word attention into the framework. As used in the HPAM model, the 2 questions will be presented by using word embeddings firstly, and then BERT-BILSTM to form the whole sentence embedding based on the context. Each BERT-BILSTM encoder is multiplied by word attention value to assign a weight for each word to extract the key points in a sentence. And the context vector will be added to attention layer to understand the sentence representation of a word. And afterward, the similarity is calculated through the weighted total of each hidden state value multiplied by its attention to calculate the final similarity score.
The first phase in our research was exploring the most appropriate embeddings that can be used in a semantic similarity comparison model to obtain the most accurate results. Word embeddings provide a dense representation of words that capture something about their meaning. Now, the existing similarity model called HBAM utilizes a method called word2vec that serves as the embedding layer to the BERT-LSTM attention layer following it. Our aim from this experiment was to explore other embedding approaches and compare the performances of each embedding model. To start off, word2vec takes as its input a large corpus of text and produces a vector space typically of several hundred dimensions, with each unique word in the corpus being assigned to a corresponding vector in the space. The model first encodes each word using one hot encoding, then feeds it into a hidden layer using a matrix of weights. The word embedding vectors are actually the weights of this fitted model. Word2vec, however, is unable to encode unknown or out-of-vocabulary words. So to deal with this problem, Facebook proposed another model called fast text. It's an extension to Word2Vec, but unlike Word2Vec, which feeds whole words into the neural network, fast text first breaks the words into several subwords and then feed them into the neural network. Using this methodology, unknown words can be represented in a vector form. Fast text was the first embedding that we experimented with. The second approach is ELMO. ELMO embeddings use a deep bidirectional LSTM model to create word representations. ELMO analyzes words within the context that they're used in. It's also character-based, allowing the model to form representations of out-of-vocabulary words. Unlike Word2Vec or fast text, ELMO does not have a dictionary lookup of words and their corresponding vectors. It creates the vectors on the fly by passing text through the deep learning model. Now the third approach is BERT. BERT is a transformer model that is trained on looking in both directions when processing a text sequence. This results in a high-value pre-trained text representations. What makes BERT different from ELMO is that transformers have set a new standard compared to RNN. Transformers improve the performance of these recurrent neural networks configurations by better dealing with the long-range dependencies between words, and also improve the performance dramatically by enabling more parallelization and training. Based on the literature and the theory, our hypothesis for this experiment is that BERT as an embedding layer before the BILSTM attention model should result in a semantic similarity comparison model with the highest accuracy. Moving on to the experiment setup and details. In order to allow comparison, the training and testing for all three embedding approaches were done on the same dataset as the HBAM model discussed earlier. This is basically a subset from the core duplicate dataset consisting of 10,000 question pairs. The dataset was divided 9:1 for training and testing. Before getting into the details of the conducted experiments, let's quickly have a look at the parameters of the already existing HBAM model. They used Google's Word2Vec pre-trained model. This was trained on Google News data. The embedding dimension, which is the size of the vector representing a single word, was 300, and the number of the epochs were 9. The maximum sequence length was 10. Meanwhile, for the fast text, we downloaded a pre-trained model called Wikinews that was trained on Wikipedia 2017. Regarding ELMO, the pre-trained model was available on TensorFlow Hub. Finally, the pre-trained model used for BERT embeddings was uncased L12. Uncased means that the text has been lowercased before word-piece tokenization. The embedding dimensions for each of the models were as follows: fast text 300, ELMO 1024, BERT 768. And after tuning, the number of epochs used for each of the models were as follows: fast text 9, ELMO 110, and BERT 100. Finally, the maximum sequence length used for fast text was 10, ELMO 72, and BERT 25. Now moving on to the results of the experiment. These graphs provide a summary of our findings. As you can see, in fast text there was no need to increase the number of epochs beyond 9, whereas BERT and ELMO required more epochs, reaching 100 and 110 respectively, to yield higher accuracies. Based on the average model accuracy values, using BERT as an embedding layer followed by BILSTM and attention layer provided higher accuracies compared to the existing HBAM model and other embeddings such as fast text and ELMO. As shown in the table, BERT resulted in an accuracy of 84.45%, whereas HBAM that used Word2Vec had an accuracy of 81.2%. Now I'll leave you with my colleague Ahmed Nasser, who will discuss further our next two experiments.
So the second experiment was basically for determining best feature extractor for text similarity model. In this experiment, the feature extraction stage that was done earlier using the BILSTM plus attention layer was altered to be performed by BIGRU attention layer. The motivation for using BIGRU was mainly the speed of the training. Our hypothesis was that training would be faster than the HBAM model used as our reference in all the experiments. The way that this experiment was set up was that the training and the testing were done on the same Cora duplicate dataset used in HBAM to allow comparison. The dataset was divided 9:1 for training and testing, and the training sector was further divided 8:2 for training and validation. The embedding layer remained constant to enable comparison, including Word2Vec, Google's Word2Vec pre-trained model. The hyperparameters used in both were as follows: number of epochs equals 9 and maximum sequence length equals 10. The experimental results of this experiment show that BIGRU leads to an improvement in training speed as well as an 0.8 improvement in evaluation accuracy over the HBAM model, given that both models use Word2Vec embeddings. As you can already see, the evaluation accuracy of BIGRU attention is a little bit higher at 82% as compared to 81.2% for BILSTM attention, and the training speed is also better at 39.8 seconds for 9 epochs as compared to 50 seconds for 9 epochs in case of BILSTM attention. This leads to the last experiment of combining BERT with BIGRU to figure if it would lead further improvements in the accuracy as compared to HBAM and BERT plus BILSTM. The way that experiment 3 is set up is that based on the previous two experiments, two conclusions were reached. The first one is using BERT as the embedding layer, which is often fed to the BILSTM attention for feature extraction, yields a higher accuracy compared to the other mentioned embedding techniques. The second conclusion is that using BIGRU attention as a feature extractor compared to BILSTM attention results in faster training and slight improvement in the accuracy. Based on these conclusions, our initial hypothesis was that a similarity model that incorporates BERT as an embedding layer, followed by BIGRU attention for feature extraction, should yield a higher accuracy compared to HBAM and BERT plus BILSTM similarity models. This is the experiment of the model that we have designed finally and that we're using for question answering, and in this experiment, the previous hypothesis was tested. The training and testing were done on the same Cora duplicate dataset used in HBAM to facilitate comparison. The dataset was divided 9:1 for training and testing. As you can already see, our BERT BILSTM attention similarity model yields in the highest evaluation accuracy at 84.45%, which is our primary evaluation here. It also yields the highest recall and the highest F1 score. This shows that the BERT BILSTM attention similarity model compared to BERT BIGRU similarity model and HBAM is way more effective. And this results, unlike our initial hypothesis, show that this specific similarity model would yield the best metrics as compared to the others. In the past few weeks, we have further tweaked the experiments done before to come up with the best possible similarity model to be incorporated in a fully functioning and accurate Q&A system. The result is a relatively new similarity model that includes BERT, BILSTM, and BIGRU. The architecture is a layered approach in which sentence pairs are concatenated and converted into their equivalent embedding using BERT. Thereafter, these embeddings are then passed twice, once for the BILSTM feature extraction layer and once again for the BIGRU feature extraction layer, to give more weight to the crucial parts of the sentences. The BILSTM layer and BIGRU layer outputs are simultaneously passed to a global average pooling layer and max pooling layer, each to retrieve the average and maximum value of each feature extracted by BILSTM and BIGRU. Both average pooling and max pooling of each BILSTM and BIGRU are concatenated together. Finally, each is then concatenated together, having the result sent to a dense layer as a final step. The following table summarizes the results for the BERT BILSTM BIGRU similarity model compared to BERT BILSTM, BERT CNN, and BERT BIGRU similarity models, tested on the iClinic question answering dataset. The results show that BERT BILSTM BIGRU yields in the highest possible accuracy of 87.19%, precision of 87.20%, recall of 87.97%, and F1 score of 87.58%. Therefore, the BERT BILSTM BIGRU similarity model is the final core similarity model included in our proposed Q&A system. And now move to Iman Yehia for details in evaluating the whole Q&A system.
So now towards the evaluation of the Q&A system as a whole. We first expanded our Q&A database. How we did that? We had collected 12 Q&A medical domain dataset. We took one of the medical domain dataset. We extracted tags from the questions and we gave the SQL our tags. Then we did a qualitative testing. How we did that? We had 466 questions. We paraphrased them. And for each paraphrased question, we compared it with the whole original dataset. So basically, we extracted from the paraphrased question the tags, took from the SQL the similar tags, send it to the similarity model, and check for the similarity. Of course, this was done after if the question was not found in the knowledge graph, as mentioned earlier. And then for the testing system, we found out that the accuracy was 86.3%. So now towards our datasets. Our dataset is divided into three main components. The first component is the knowledge graph dataset. Secondly is the similarity model dataset, and finally is the medical Q&A dataset. The knowledge graph dataset. The knowledge graph is developed by Neo4j with the data from the Health Navigator New Zealand. The original knowledge graph had 2,900 entity, and we have added 100 new entity, which led to a total of 3,000 entity. What we mean by entity, we have added new diseases, symptoms, departments, and so on. Additionally, the knowledge graph originally had 5,000 relationship, where we have expanded it using new relations such as symptoms related, i.e. the user can enter a question, for example, he or she has fever. So the system returns they might have COVID, cold, and so on. Also, we have added a new relationship called combined relation. The system originally returns symptoms or definition. Now the system can return both together. So this added up to 1,000 new relationship. And all this expansion was used using New Zealand Health Institute dataset. So our new knowledge graph now has 3,000 entity in total and 6,000 relationship. Now towards the similarity model dataset. As discussed earlier, we had two different models, and for each model we had different datasets. So for BERT-BILSTM attention similarity model, we trained it using Cura duplicate question dataset. The dataset is divided into 3 columns, 2 columns for question pairs and 1 column whether they are duplicate or not. If they are duplicate, it was indicated using 1, otherwise it's 0. And the dataset contained 400,000 duplicate questions. While for the second similarity model, which was BERT-BIGRU and BILSTM similarity model, it was trained using Stanford Natural Language Interface SNLI corpus dataset. So basically it was divided also in 3 columns, but now instead of having question pairs, it is sentence pairs, and instead of having its duplicate or not, it has a column for similarity, and the similarity it had 3 options, 3 labels: neutral, contradiction, and entailment. And the dataset contains 570,000 human written English sentence pairs. While for the medical question datasets, we have collected 12 question and answer pairs dataset, almost 2,460,000 question and answers. All this was collected from eHealth Forum, iClinic, Question Doctor, Q&A, and so on. Nevertheless, also we found COVID-19 question and answers pairs. Basically, the dataset was divided into 2 main columns, column for the question and column for the answer. While for the diseases frequently asked in our testing dataset, we found out that 24% was coldness, 13% was fever, 11% was anxiety, 8% was diarrhea, 6% was depression, and finally 38% was others. What we aim to do is to use the 2.5 million dataset collected in the medical domain and to expand our dataset, filter out the most common question asked, the diseases, and to make it more specific domain.
We have made a simple GUI to demonstrate our Q&A system. Here I will go with a few examples of questions to show you how our Q&A system will respond to it. The first question is, what is coronavirus? As you can see, the Q&A system successfully responds with a definition of coronavirus. I can also ask the same question in different forms. I can say prevent lung cancer, and it will come up with the precautions one can take to prevent lung cancer. And I simply ask how to avoid lung cancer, and it will come up with the same answer to the similar questions. Now I will go through the CAPSTONE reinforcement outcomes and what we have achieved so far, and discuss further work we believe can be done. We have achieved the 2 parts of our research milestones by developing a high accuracy similarity model and submitting a related paper for publication. This paper is initially accepted for examination by the IEEE Conference Examination Committee. We also finished a fully functional medical Q&A system and wrote a second paper highlighting the system components and our work in it. We are now further improving the paper to submit it to the ACL conference by mid-May. Finally, we want to highlight what we believe can be done building on our work. We wanted to use duplicate medical question dataset for specified training. However, we have spent a lot of time searching for adequate medical datasets to train the model on, but we ended in not finding any. That's why our model is trained on general duplicate questions dataset. We want to explore more the results of our similarity model if it's trained on specific data.
if a new data source is found with good duplicate medical questions. Our system is trained on English datasets, making it only responsive to English questions. We want to incorporate more languages into the QA system to make it able of answering medical questions in different languages. The last thing is to add speech recognition to the Q&A system to enable the user both to speak and type their questions. Here are the references for this presentation, and thank you. We are ready for your questions.